Yeah, so my talk is Riveting Insights, Bridge.Watch and the State of America's Infrastructure. So really quick, what I'm going to cover in 10 minutes, the motivation and background for this project, how I gathered the data, building the framework, a little bit about building maps on the web for free, and then the insights that I gained from this project. So a little bit about me. I started my career as a structural bridge engineer, and then eventually I switched to buildings, and then eventually I switched to software. So I worked on a lot of large infrastructure projects and big private projects like museums. And these are projects where commercial software really falls short, and most commercial software for the built environment is terrible. So I wrote software to fill in the gaps. So I've made a switch to working on digital infrastructure, working on expanding broadband in the US with Ready.net. But I still have this frequent frustration that structural engineers are really bad at explaining what they do. Architects often get credit for like what a structural engineer does. And so I found software as a way to show structural engineers' impact on the built environment, particularly through sustainability and embodied carbon. I really like to work with public building data sets, permit information from city open data. So in terms of where I got this data set from, there's actually the Federal Highway Administration for the US has this national bridge inventory, and it has CSV data going back 30 years. So it's about 500,000 bridges. There are also culverts and tunnels in the data set, but I ignored those. So I started on this project when 1992 data was still on the website, but it vanishes off their website once it hits the 30-year mark. So this data is encoded using this left-hand standard, which is the recording and coding guide for structural inventory and appraisal of the nation's bridges. So this is a giant CSV that you can download for each state. And now they're actually switching to a different standard in 2028. So we'll see how they do that data migration. But hopefully this is going to be a more sane format because I spent a lot of time cleaning the data that I had. Another aspect of this project is that there is a web interface to see this data. So it's the Long-Term Bridge Performance LTBP Info Bridge web app. The landing page map isn't that great. It's got raster tiles, it's kind of ugly. It takes quite a bit to load. It's not the best performance. And I think probably most importantly, if you want to look at everything, it only has 2 sets of data for a lot of views. And it's from like 2020 and 2024. One thing that you can do on this website is you can track a bridge condition over time. So if you want to look at one specific bridge, you can get like a nice little line chart that has its condition. But you can't really fine tune aggregate calculations, and the geospatial stuff just isn't that great. So this is motivation to build a better aggregate data visualization with better filters. So where did I start? I have been traumatized by Excel from using it to design skyscrapers. So I decided to do all of my data cleaning and processing with Visitdata. So I got the CSV data from FHWA. So Visitdata is fast, it's open source, it's using pandas under the hood, and it looks really cool because you're interacting with it in a terminal. And I was able to use that to figure out which fields are interesting to show. So looking at the condition, the year built, inspection dates, and then traffic rates. And then I used Observable for a lot of prototyping with D3 and landed on some advanced filtering based on what I knew was useful for my time as an engineer. And what was really important to me with this project was to make it interactive, so you can kind of like toggle on different things and like mouse over different areas. So in terms of what the actual framework is, this is just a pretty simple web app running on a DigitalOcean droplet, using PostGIS for spatial queries, not using it too much right now, just a basic Django backend, and using Node.js as like an aggregator layer for D3. And then I have a blog about this that I'll show at the end that has more technical details. So what I landed on was using 3 different aggregate visual types. So this is a scaled hex bin where you can interact with different hexes. And then I also have these chloropleth aggregate maps and an interactive sunburst map. And so each visualization stores its set as a query string so you can pass around settings. Yep. So in terms of the mapping part of this, outside of D3, so I did not want to pay Mapbox or Google Maps or have to set up my own tile server. So I figured out this pipeline going from GeoFabric, where you can download OpenStreetMap data and then create really nice vector tiles using Planetailer. And then with Tippecanoe, I added the bridge data set to the tiles. And then I used protomaps and the PM tiles format. So I actually just have a static file that's hosted on my droplet, and the tiles are retrieved using HTTP range requests. And then in terms of the library I'm using for the map, the front-end library is MapLibre. So this is an open source fork of Mapbox GLJS. And this is where I get like all of the UI components, like the zoom, markers, overlays, adding in like the building styles that you would see on a map. So what did I learn from this? Some of the disclaimers, there are no rail bridge ratings. The years are included though. Pedestrian bridges are largely missing because both of those types of bridges aren't, inspected by the Federal Highway Association. And then you might have heard you might have heard the term structurally deficient or functionally obsolete used to describe like bridge conditions. It's outdated terminology and hasn't been used since 2016 because I think it was confusing that people or like politicians were using it to say that all of our bridges are falling down. So what I learned from this is that things aren't that bad. When I got the initial data set, the first visualization I built was basically tracking the number of poor bridges. And started with 1992 data, ends with the 2021 data. And the percent in poor condition dropped from 18% to 8%. And a cynic might say like how they rate the bridge has changed, but that encoding hasn't changed since 1994. If you want to know more about this, I recommend reading Construction Physics article, which is like the worst US bridges are getting fixed. Basically, the takeaway is that bridges are just becoming more average. Other insights that I wanted to gain from this project, like what does the choice of material for a bridge tell us? When I worked on buildings, it's not really, like the choice of material is often determined by factors that you wouldn't expect. Like it can be based on unions or politics. Like most skyscrapers in New York City have been built out of steel, but skyscrapers in like Miami are mostly concrete, and that has more to do with trade unions and available labor than whether the material is better. So I was kind of not surprised to see this, but steel bridges are a lot more prevalent in the eastern half of the US, but obviously there are lots of concrete bridges on both coasts. This gives you an example of the histogram of the relative ages of the bridges. So steel bridges are quite a bit older than the concrete ones, and there's definitely been a decline in the number of new steel bridges that have been constructed. I also took a look at just looking at Western states versus states in the Northeast. So red is the steel bridges, and blue and purple are different kinds of concrete bridges, so they're all concrete. So there's a higher proportion of steel in the Northeast, but concrete dominates in the West. That might be all those elevated overpasses in Los Angeles. There's similar peaks in terms of construction year because of like prior investment in the highway system. Also, what bridges are the most critical? Like what types of bridges and what material? So still ended up looking more into steel bridges, and then I focused on steel bridges because about half of the most heavily trafficked bridges in the US, so those that have more than 50,000 cars on them per day, are steel. So the other interesting thing is that most long span bridges are also steel, so 87%. And then when you look at these long span steel bridges, they are on average 40 years older than other long span bridges. And this is kind of not surprising, but most of the long span bridges in the US follow the Mississippi River system because the width of the river is 4,000 feet at its widest point. But what's interesting is looking at trusses in particular is that trusses are more likely to be labeled fracture critical. So when these truss bridges were built, they made sense for being long span because they're easier to build and to move into place. You can either launch them from the shore or build them in pieces and then assemble them in the center. But the downside is this fracture critical rating means that a loss of a single member can cause an actual collapse. And one of the things that you can see in the data set, these long span steel bridges, due to recent events, and I think just in general, they're often inspected more often than others. Most bridges are on a 2-year inspection cycle. When I first built this, one of the questions I got most from people was, what about the bridges around me? So as I changed into working on mapping and geospatial, I actually built this interactive map that has some fun with like 3D hex bins for the overall view. So this is showing similar data to the original map where it's just the overall condition. But this also allows you to select nearby bridges and see what the state of infrastructure is near you. And so you can get more insights into the type, span, and material similar to some of the other visuals that I showed. Okay, and you can access this and play around with it. It's at Bridge.Watch. All the code is hosted on GitHub, and you can find me at my portfolio website or on Mastodon. Yeah.